Hello again, physics friends. Today we're going to talk about a particle on a tabletop with a central force, and we're going to use the Lagrangian formalism. Now, typically, we have been up until now using the Lagrangian to solve for a specific system, but here we're going to expand our discussion to talk about a whole class of systems, and that class of systems are called central forces, and we'll define what a central force is. And we'll show, using this derivation, that we end up with the same equations of motion that we did when we talked about Newton's law in 2D polar coordinates. So let's get into that. First, we're going to draw a diagram of the system, which looks like this. So here we see in purple our particle at a position vector r, and this particle is subject to a central force. So let's make sure we understand what a central force means. So here we basically are saying that the force on this particle is either pointing towards the origin or away from the origin. In other words, the force is either parallel or anti-parallel to the position vector, like so. And we could, I guess, use x and y, the Cartesian coordinates, to talk about this problem, but given the symmetry in the problem, it's much more sensible to use 2D polar coordinates. So our 2D polar coordinates are the distance from the origin and the angle with respect to the x-axis. And what we'd like to do now is write down the Lagrangian for the system. Even though we haven't specified the details of the force, we're just going to write it out for an arbitrary central force. And we want to highlight some of the key ideas that will apply to all systems with a central force. Here we go. So as always, we could start by writing in Cartesian coordinates, but eventually we want to go into our 2D polar coordinates. So we have our two generalized coordinates. In this case would be r and phi. So to go from Cartesian to our generalized coordinates, we want to write our Cartesian coordinates in terms of our general coordinates. We can take time derivatives, square them and add, and we'll find that all the trig functions go away and you're left with r dot squared and r squared, phi dot squared. So we can write the kinetic energy in using polar coordinates as m over 2 r dot squared plus r squared phi dot squared. That's our kinetic energy. Now our potential energy is not fully specified other than to say that it's some unknown function of r. So the potential depends only on r, not on the angle phi. Okay, so our full Lagrangian then is t minus u, which is the following. Okay, and it does not depend rather on phi. So there's no phi dependence. So let's see what the consequences here are. So here we know that if there's no phi dependence in the Lagrangian, then the partial of the Lagrangian with respect to phi is 0, and the Euler-Lagrange equations then tell us that the momentum associated with the phi is constant. That would be the angular momentum due to the motion that's not radial in this plane. This comes out of the Euler-Lagrange equations. Perhaps you're comfortable just seeing that right now. In other words, the partial with respect to a generalized coordinate represents the generalized force, and therefore the associated momentum will be constant if that force is 0. But let's just go step by step and compute all of the partials and construct the Euler-Lagrange equations and show that that's true. So we start with the partials with respect to position r, the r coordinate rather, and r dot, and we find the following two terms. When we take a time derivative, we find mr double dot. So the Euler-Lagrange equations are going to equate the first partial with the third term here. We'll move on to the angular terms next. And as we already pointed out, the partial with respect to phi is 0. The partial with respect to phi dot is mr squared phi dot. And let's just make sure that we understand that this mr squared phi dot is like the angular momentum. Okay, so in this diagram we have in the xy plane, we have the object, the position vector to the object, and a velocity vector for the object. And we know that the angular momentum is given by r cross p, which is r times r cross mv, and we can factor out the m, which is constant, and then we have r cross v. So how do we think about r cross v? Well, we can talk about, mag r mag v sine of the angle between, but we can also think about which component of the velocity contributes to the angular momentum. So if we break up the velocity vector into a radial piece and a tangential piece, we know that the radial piece does not contribute to the angular momentum because it's parallel to the position vector, and r crossed into something parallel to it will give you 0. So only the tangential component of the velocity will contribute to the angular momentum, and the tangential component is equal to r times omega, or phi dot, the rate of change of that angle. Okay, so when we write down the angular momentum, it will have a magnitude that's equal to m times r phi dot, or m r squared phi dot, which is exactly what we have here. Okay, so this this term here is the generalized force in the phi direction, and then this term here is the momentum in the phi direction. Similarly, this is the generalized force in the radial direction, and this is the generalized momentum in the radial direction. Okay. So we see that the Euler-Lagrange equations will have one for r and one for phi, take this following form, and we can just plug in the values we've already found and see what we end up with. And when we do that, we end up with the following: mr double dot equals this right-hand side. And this is starting to look familiar. Remember, if we bring one term to the left-hand side and leave du dr alone on the right-hand side, this is exactly what we had for Newton's second law in 2D polar. At least that's what we had for the radial component. So it's m times the radial acceleration equals the radial force. And we expect to find the same thing for the angular piece, so let's do that next. So here we have the Euler-Lagrange equation for the angle phi. And because phi is an ignorable coordinate, meaning the partial of Lagrangian with respect to it is 0, the Euler-Lagrange equation looks quite simple. It says there's a conserved quantity. This we already showed was the angular momentum. And the time derivative of angular momentum being 0 tells us that angular momentum is conserved. Okay. And so usually we'll just leave it in this form because it's nice to leave it in a form where we know what a constant, what quantity is constant. But here we're going to expand this out, and we'll take the time derivative and see what we get. So we have a 2mr dot phi dot, but then we have a product rule plus m r squared phi double dot is equal to 0. And when we move things around here, we'll end up with m times r phi double dot plus 2r dot phi dot, all times r equals 0. And in general, we're going to be away from the origin. In that case, we can ignore the r equals 0 term. Or if you like, divide through by r, and we get the following, which is Newton's second law in 2D polar, but for the angular piece. M times the tangential acceleration is equal to the net tangential force. But in this problem, we only considered central forces, and so the tangential component of the force will be 0. So in the Lagrangian approach, we would say angular momentum is conserved because phi does not appear in the Lagrangian. Using Newton's second law, we would say that the angular momentum is conserved because there's no torque, right? The force is purely radial. There's no tangential component to the force, That's what we're seeing here. Therefore, there's no torque on the system, and if there's no torque, then the angular momentum cannot change. So this exercise is a nice preview of what's to come, and in particular, we're going to start talking more generally about central forces between two objects. In the case here, we're talking about a central force directed towards the origin, so it's a one object system that's pulled towards the origin, but we're going to extend this soon to talking about two objects and the central force in between them, meaning that the force by object 1 on object 2 is directed towards or away from that object. So if you have object 1, you have object 2. Object 2 is going to feel a force that's either towards or away from object 1, which means all of the forces are parallel to the line connecting objects 1 and 2. And we're going to show that even though that system is two particles, which in general you might imagine requires 6 degrees of freedom, this actually simplifies to a one-dimensional problem. And we're going to write down the Lagrangian for that one-dimensional problem and talk about effective potentials, and we'll talk about the dynamics of these systems. So one kind of concrete version of this would be the sun and the earth. In that case, both the sun and the earth move, and we can talk about the motion of that system. We're going to learn that all of this motion is planar in the same way that the problem we just did today was planar. And we're going to learn about what kinds of orbits that you can have in a system like this, not just for gravitational systems, but any system where the only force between the two bodies is a central force. So we'll get into that more in the coming days, but until then, take care and be well.